Equals MC squared.
No, it's
I also
the
got
distance
A.
squared.
The
distance matters.
Why don't you use a
Okay. Here we go. So today is kind of going to be like a combination and kind of summation of a bunch of things that we've done. So imagine this. You have a thin rod that has a negative end on it.
Q equals. Sorry.
Imagine that you have a thin rod. You have a negative end on one and you have a positive end on the other. And they're separated by some length L, and you're going to submit that into an electric field that's pointed up. Okay? So imagine this. Okay? Here's this rod. You have a negative end on one side and you have a positive end on the other. Okay? And then you're going to have an electric field that's pointing upward. Okay? So, Wyatt, are you going to say something? So what's the negative end going to feel?
Down.
Why?
Because the electric field is on a positive test charge. Negative is outwards.
Okay? So the negative end is going to feel pulled down. Okay? What's the positive end going to feel? Pull. So push up like that. Now, does anybody remember the formula for torque?
What?
Well, that's part of it. Force times radius.
For real.
Right? For real. Okay. Now, here's the deal. If you know the charge on this end, and assuming that it's going to rotate about that middle end like this, okay, like a baton. So if that's going to rotate about that middle, about this end, how could you calculate the torque that's acting on that positive end? So you have to have two things. You have to have force and you have to have radius. But it's in an electric field. Okay. So how could you calculate the force acting on that positive charge? Right?
Equals
F.
Q.
True?
Yes.
If you know the electric field and you know the value of the charge, that's going to get to the force part of it, right?
Yes.
Okay? Now, the radius has to be from the center. So the total distance between the points is L. So the radius is going to be
L
over 2. Okay? Right?
Makes sense.
So this side, the positive side, is going to get pushed up. So this is the force that's on the positive side. So how could you find the force on the negative side? Exact same thing, right? Okay? That would also equal F times L over 2. Now, let's just say I'm only going to push on one side. If I were only going to push on one side, like for example on that positive side, if I were going to push that up, that would just be the force on that positive side, F times L over 2. But not only is this side getting pushed up, what's happening to this side over here? That side's getting pulled down. So they're going to be working in the same direction, right? So one torque's going to be pushing it up, the other torque's going to be pulling it down. So, how do you think you can find the total torque? Add them together. Or multiply this by
EQL.
Or
2.
So it's
No
just
way.
Or just put L instead of. Oh my goodness.
So the torque equals echo.
Wow.
Okay?
Echo.
So they take advantage of this to separate, like some medicines. This only works if you have what we call a polar molecule, like water, for example.
Wait, this is water or
So
spinning?
if it's a polar molecule, this doesn't work if the molecule is neutral. But if there's a positive end and a negative end, you can submit this into an electric field, and that would make it twist. Now, yes, Olivia,
Okay, wait. Explain why do they multiply by 2?
because
I-
this side is being pushed up. Cool with that. The other side is being pulled down, so they're working in conjunction with each other. So the total force would be this one because they're going in the same direction. Okay? So that's why you can either add them together or multiply by 2. It's the same thing. But if you had like one side pushing it down and the other side pushing it up on that same side, then there would be no net torque. But since they're going in the same direction, we can add them together.
Okay.
Makes sense?
Yeah.
All right. So you can use this then to separate polar molecules, or at least get them to line up. Because eventually what's going to happen is that this is going to swing up, this is going to swing down. Okay? Now, what would happen if you have that positive charge up here and that negative end down here, and it was lined up with the electric field? Bless you.
The other way.
What would happen?
It wouldn't spin.
It
Oh,
wouldn't
it's spin the other
spin,
way. Other way.
but would it move up or down?
No.
It
You
would
didn't say the field is constant.
I'm just saying there's an electric field acting upward. So think this through. Think this through. Let's start with the positive up there at the top. If the electric field is pointing up, what's the positive charge going to feel? So it's going to feel pushed up, right?
C.
What's the negative end going to feel?
Down.
It's going to feel pulled down.
Oh, it
But
won't
it's
spin.
closer, so it's going to be pulled more.
Well, no, this is just the field. You
how
always
is it
assume the electric
spinning?
field is constant.
Oh.
You're just in an electric field. You don't know what the source is. This is just you're in an electric field. You don't assume this electric field is constant.
Oh.
Okay.
Nothing's moving.
So what's it going to do?
No.
It's going to be like a string, and it's going to get stretched.
Mm.
Now, interesting thing happens though. If you stretch it, are you going to do work on it?
Yeah.
Or so we're just
Works
Work.
like a lefty.
So where's the spinning coming from?
That's
It
if
only
it was
swings
crossways to it. If it was at right angles to the electric field. But then it's going to spin, and then it's going to get lined up with it.
Oh, okay. So you're saying that. So you're saying when it gets started,
Yeah, so you're going to start like this, it's going to end up like this.
and then it stretches. Okay.
And then it's going to stretch.
Oh! Oh, I got it. No, it's like a
His
click.
brain is growing.
Go on,
Stretching.
Adam. Adam,
There's
His brain's getting another
you
ring.
know ball.
It's getting another.
No, and I'll tell you why there's some validity to this. Okay? I don't want you to scream or do anything or take. But what they figured out is that for you to when you actually learn something, your brain does fundamentally change its structure. No, it does. Because you build a new neural network. But what they figured out, and this has kind of changed how, to a certain degree, how I approach teaching, is that you won't learn it like the first time. But it takes at least 2, 3, 4 times to physically build that neural network. Okay? So this is why we're like, oh, repetitive is boring. Not if you look at it from the perspective that if I just tell you one thing one time, you're going to begin to build that neural network. But if you repeat it again and again and again, you physically build that neural network, and then that synapse, which is the connection between the neurons, becomes more efficient. What, Nathan?
If our brain continues to expand, right?
No,
eventually-
not expand.
Not
You're
expand.
just building new pathways within it.
You're getting a new
But
ring.
If we're
Once
building
you
it,
get a
we
Mega
destroy
Mind.
something
Mike.
else to keep the same amount of
Your
power.
mic.
So if it's
It's like a
study-
penguin.
If I study physics, then I
Eventually,
lose
when
my
you get
linear
old enough,
rubber.
Shan.
it starts destroying it.
Can you like take the dreads off of your face real quick?
Take the dreads off of my face.
There's no correlation.
Where are we going with
What?
What's the
that?
correlation?
You look easy to draw though.
Never mind. Go back to teaching. I don't want to.
Red card.
Look what you did, Louise.
Make him stand a 3-minute flag just to
Mid-conversation. So when somebody says that,
Dude, I had to.
you're
I
making
think
the
that's
connections. Your brain is literally making
You are
connections.
literally building a new connection. Right?
Oh,
You are
man.
literally building, you are fundamentally changing the structure.
That's pretty crazy.
Okay, now, next thing. So if you look at kind of what makes your modern day life exist, one of these is this equation right here. Okay? Even though you've never seen it.
That sounds looks quite good.
So what this is the electric field that exists within a capacitor. Okay? Now, so what's on the physics sheet, okay, where it has E sub C, and then it has the Greek letter cow, epsilon naught A over D. Okay? So, or excuse me, yeah, Q K over epsilon naught A. I was looking at the wrong one. The electric field within a capacitor.
Oh, I see.
It says E sub C. Okay? Now, let me explain how this functionally works. The Greek letter cow is a constant, okay? And it has different numbers of 1, 2, 3. Why they put this in here, I don't even know. I've never seen a problem where cow is anything other than 1. Okay? So, and if you look on it, it'll say like what K is if you find it. If you come over here, it has like this Greek letter, it should be on here, yeah, this dielectric constant. Just assume that it's 1, okay? Don't flip out. I've never seen them do anything but 1. Now, let me kind of show you how capacitors work. So capacitors make your life possible, because without capacitors, your cell phones wouldn't work.
They hold the charge.
Right? Yes. Capacitors are kind of like batteries. All right? So
Regulated.
here's let me
I learned it in
this whole
HVAC.
setup over here.
But what's the thing like when it overcharges and like it pops?
Okay. So let me kind of explain what this setup is.
It's holding a
So I've got this capacitor. So capacitors are rated in farads.
Yes, it
So this is a 100 microfarad capacitor. Okay? So this is 1,000 mu sub F. Okay? Which stands for 1,000 microfarads. Don't worry about the number, you just rate capacitors in farads. So basically, the bigger the number is, you can think of it as being like a dam holding back water. The bigger that is, the more water you can store behind it. Okay? Now, but just like to fill the dam, you need to pump water into it to hold it. The same thing is true of a capacitor. So, what I'm going to do is that, to show you that this capacitor has no charge, I've got it hooked up to a blue LED light. So if I close this switch, you'll notice that the light does not come on, it's off. So what I'm going to do is I'm going to open up that switch, and then I'm going to connect this to the capacitor. So by doing that, I'm hooking up to a battery source. So what I'm doing is pumping water behind the dam, okay? So I'm building that up. So when you plug your phone in at night, to a certain extent, what you're doing is that you're charging up your capacitors, okay? So this is holding a certain amount of charge. I've got that capacitor charged. Now, I'm going to disconnect it. So now it's just like I've shut off the water. I've got the water behind the dam. So what I'm going to do is that I'm going to close this switch. And when I close that switch,
Wait a
you
minute.
notice that that light briefly went on. Okay, so let me do it again.
So you always have to touch like
Okay.
a screwdriver to touch
But if
capacitor.
you only hold it,
They hold the charge.
So I'm going to hook it up to the battery, and we've got it charged up. Okay, so it's charging this thing up. It's putting the water behind the dam. So within this capacitor, there's an electric field. Okay? So what you're doing is building up an electric field within the capacitor. So what that means is that a capacitor has like a positive and negative side to it. Okay? So what you're doing by charging it up is that you are pushing and creating this separation gradient. It's kind of like your car battery. If your alternator doesn't work on your car battery, your battery goes dead.
Yes.
It drains it. Okay? Because there's no capacity to recharge your battery.
See.
So this capacitor won't charge itself. You have to do some work on it, which is coming from the battery. So the battery is creating this difference, it's creating this electric field. Now think this through. If, let's say, the top of this capacitor plate, call it a parallel plate capacitor. If the top is positively charged and the bottom is negatively charged, what's the direction of the electric field in between those two plates? Pointing down or pointing up? Down. Why?
Zero.
Yeah, because if you put a positive test charge in there, what's going to happen? Yeah, you're going to have two things happening. It's going to get pushed down by the positive and attracted to the negative. So the direction of the electric field is in this direction. So what happens is that when I hook this thing up, okay, what I'm doing is I'm creating this potential within the capacitor, okay? So it doesn't hold much, like, oh, my battery is dead. Let me go get Burkham's 1,000 microfarad capacitor. I'll start my car, okay?
No, bye-bye capacity.
Okay? But, so, Alyssa, watch the blue light, okay? So you can see this, right? So I'm going to close this switch. When I close that switch,
Yo.
you get this.
I look, you can't see. His face is in the way.
Okay, hold on. Let me recharge it.
No.
Well, it's just a tiny light. It isn't like we're looking at the moon. So,
The moon just has to.
Yeah.
Hey, I can
Yeah.
feel like.
okay, you ready?
Yeah.
Gotta said that.
Hold on, sorry.
Get it, we're
didn't hold the charger.
We broke physics.
We're gonna need like 5 minutes to take a bath.
There you go.
You might be the least important person in a jumping night ever.
I'm the you might be what?
Wait, what?
The least important.
Hey, Shannon,
Never mind.
Shannon,
Hey, I'm gonna be group leader. I'll try to. I got the blueprints for
You were
the
gonna
bro.
be used as bait.
Exactly,
We're
exactly.
following you out there.
Hey, why?
Gonna be used as a
Hey,
weapon.
why?
Exactly. I bait him in, and you guys jump
Nathan.
on.
Why?
Nathan, he'd probably be used as a weapon.
You seen that? The young
Okay,
guy-
so
swinging
you ready?
around.
Hey, I don't want to hear Kevin talk.
Hopefully
I don't want
she
to
can
hear
charge
Kevin.
it. Ready?
Yeah,
Boom.
Go kiss us.
Okay.
Oh, this is just you.
Yeah, yeah.
So,
Really?
it doesn't hold much charge. But here's an interesting thing, and we'll talk more about this when we get into circuits. What quit?
Upgrade now.
To use
If you press upgrade and then press the X, I think it works.
So upgrade it and then we get
Yeah.
premium.
There should be a big X.
No, no, no,
Yeah,
no,
press
no,
it
no,
and
no.
go, oh. See what's included.
Let's see what's included,
Hey,
bro.
just use a free plan. Basic plan.
Oh yeah, pay $150 for like.
Oh no.
Hey, put that on
That's gotta be the
Put that on
biggest
Bot's
mistake
tab.
I opted. Get his credit card number.
Yo.
Yo, Bob.
What do you do, fire me? That's a good trump card to have, by the way.
What's a good Trump card?
Shut up. It takes probably like 4 years to replace one.
Hey, Gavin won't understand the joke.
I just
Those are big laptop
so-
changes.
Thanks for the note.
Okay. So, what the capacitor is doing, building up charge. So if you look at this equation where you have EC equal, and I'm going to write it out like you have on your equation sheet. So that's quit. Q over cal epsilon naught A.
Why is it called?
So Q is just the amount of charge that's on there. So obviously, if it isn't charged up, there's no electric field in it. Okay? This is this dielectric constant. It's just 1. Don't worry about it. Now, the epsilon naught is a constant. This is what's on the back side of this sheet, And if you come over here, you have this, it is called the vacuum permittivity constant. There's vacuum permittivity and vacuum permeability, okay? It'll play out large once we get into light and electromagnetic theory. For now, just accept it as a number. So you have epsilon naught, which is 8.85 times 10 to the negative 12th, and technically it's Coulomb squared over Newton meter squared, okay? So your epsilon naught is a fixed value, okay? So typically how this plays out in terms of how you use it, it's just usually just Q over A over epsilon naught. So think this through. Functionally, the area on a capacitor is going to be a fixed value. That's the area of the two plates that make up the capacitor, okay? You can't change that. You can't change epsilon naught. So the only thing that you can really change is the area, is the amount of charge that you put on it. So the area and the epsilon naught are basically fixed values. So the more charge that you put on it, the greater the electric field within it. Okay, and the greater the electric field is, the more work that you can do. Okay.
Are we doing a lap today?
Now,
Wait, Burkham.
what?
Capacitors have like a shut-off switch, like so it won't purposely go on.
Yeah, so basically,
Because one time I blew mine up.
well, so if you look here, let me show you what happened. So I'm going to hook this up, and I'm going to leave that switch closed, and then I'm going to hook it up to the battery.
Uh-oh.
It's gonna blow up.
No, it's not going to blow up. Okay?
Bye, Mr. Burkey.
Okay? So what happened was that very briefly, when I threw that switch, that light came on for a brief amount of time. So once we get into the circuits, this will make more sense. Electricity always takes the path of least resistance. So what was happening was that initially this capacitor was being charged. Once it got charged, it diverted some electricity up to the bulb. That's when that came on. But then basically there was so much resistance because the capacitor was charged, and now basically there isn't anything left to push that through. So that's why that bulb went out. So one of the things you could do is when we get into circuits is we can use LED lights because they're simple, they're cheap, and they work well. So we can use that to determine, hey, is electricity flowing or not, based upon a simple LED light. Okay. So give that a slight bit of a turn. All right. So charge the first balloon.
Oh, more balloons. What are the chances I hit this balloon here by pencil?
The same
What are
thing.
the chances I send you to the office if you try?
Never, because I'm never going to throw my
favorite.
So I put my hand here. Oh, come on.
That is 0%.
Is it humid?
Huh?
It's 0%. It's your favorite student.
Oh yeah, it's 0% because I'm your favorite student.
No, that wasn't. You were.
Hey, Jack,
It's
the more
humid
you
today,
talk,
Mr.
the more you
Burkham.
bring it, the more humid it is. You're
It's really humid.
In a track.
We got a little bit going.
Oh!
Okay?
Sorry.
Got a little bit going. Now, I need that. Now I'm going to charge
Did you give it your positives, bro?
Hey, what hell?
this balloon. So, put them together.
Ah.
Okay?
Ooh.
Now, as that gets pushed away, like that, is this creating an electric field?
Yes.
Yeah.
What's the direction of the electric field?
Inward.
Away.
No.
Inward.
In. Why?
This is
So it's negative.
Because if this
Yeah.
is negatively charged, I put a positive test charge. Gonna feel this, right?
For Dollar Chocolate was.
So this is creating an electric field inward, right? If that's negatively charged,
Yeah.
that's creating an electric field also inward, right? So now, but if you put a negative charge in between, it's going to feel repulsed.
Yes.
So this is why this is going to get pushed. Now, I don't want you to focus on this one. I want you to focus on this balloon. Okay? So let's assume this balloon is out here like this. Now, you don't have to worry about the buoyant force acting on the balloon. Glad tomorrow you will. But for now, you don't have to.
In physics honors, we didn't do buoyancy.
So that took in physics honors.
Cry me a
I think I'm
Okay, it was one equation. Okay,
Hey, I'll
Hey.
teach it. I'll teach it.
it was one
Oh,
equation.
yeah, I'm good.
We took a week on it.
I'll teach you guys.
You don't have to worry
I
about
don't trust
today's
why-
assignments. Show up.
Okay.
Okay, so let's just focus on this, assuming that there's an electric field. Okay? So, if this is negatively charged, and let's say this balloon is out here like this. If this is negatively charged, is the electric field going from my left to my right, or is it going from my right to my left?
What? Just hear me first.
Okay.
What did you say?
Let's assume that this balloon is negatively charged.
Uh-huh.
And you see it hanging out here like this. Okay? Not straight down, it's off to an angle.
Okay.
Okay?
Left to right.
This is negatively charged.
Uh-huh.
Cool?
Yeah.
So here's my question. Is the electric field going to your left or going to your right?
My right.
All right.
Why?
Because it's literally going this way.
It's attracting the electric
Positive.
field.
The
So if you're in the
positive
middle, it's going to be
goes
the right.
Towards the
Attracted
That's
to
positive
something.
test charge
Hold
to
on.
be attracted to it.
Back up the bus.
Okay.
If the balloon was positively charged,
Yes.
start with this thought process.
See.
If the balloon was positively charged and the electric field was going in this direction,
Uh-huh.
what would it feel?
Repulsion.
It would feel pushed in that direction. If the electric field is going this way,
Oh, it's going to
and if this was positively charged,
Other way.
the electric field would push it that way.
Other way. Other way.
So if it's negatively charged and the electric field was going this way, what would happen? It would go this direction. So if this is negatively charged, that means the electric field is going in this direction. Okay. So if you know the charge on the balloon
See.
and you know the strength of the electric field, what could you find?
That's-
Force. Right?
Yeah.
You have it?
Sorry, he was asleep, so I was waking him up.
So
I'm trying to make him learn. So he's not.
the electric field's going to be going this way.
See.
What other forces are acting on the balloon?
Force gravity.
Gravity acting which way?
Downward.
Down.
Straight down?
Yes.
That's an angle.
What else you got?
Aries is.
No.
Tension.
The string.
Force
The string.
tension.
Tension. String.
Ah, the tension of the string. Ooh, right?
Canceling out force gravity.
So, when you have a charged particle at an angle, like this, okay?
I have a job.
So,
Have a job.
9 to 5.
You have a job. Maybe an internship. You have an
9 to 5
internship or a job.
Hey, why? What's it 9 to 5? Buddy?
so the tension's going to try and pull it up like this, right?
Pay attention to what's in your life. Oh yeah, this is all my fault, Chan. He's staring at you.
He's looking at you.
What else you got?
Gravity.
Force parallel. Wait, no.
Okay? Now,
Brains are shrinking, bro.
think about this. Let's say you had a thing going around in a circle like this.
Centripetal force.
Don't say that again.
We all
I'll
hate.
bring it back.
Take it back just
So, if it's a rubber stopper going around in a circle, what are the three forces acting on the rubber stopper?
Tension.
Gravity.
Centripetal.
Centripetal.
The gravitational force
Centripetal.
and the centripetal force. Which direction?
Inward at a 90 degree angle to the back.
Oh! The centripetal force is going to act like this. Right?
down.
So the only difference is that instead of centripetal force, you're going to have the force from the electric field. Okay? Now,
You're walking on real thin ice.
Getting there.
of the three, which do you think is going to be easiest to measure?
Gravity.
Gravitational force.
Yeah.
Now, let's think about this. If you know what the gravitational force is, and let's say, for example, you know that that's, say, a 15-degree angle. All you know is the gravitational force.
All you need is science.
Okay? If you know that's your gravitational force, could you find the other two?
See.
So if you know one of these values and that angle,
You find everything.
you can find the other ones. So if you come back here and redraw that a little bit and go, oh, okay, here's my FG, right? And then that's the force from the electrical field. Okay? So if this is 15 degrees, what would be the angle on the outside?
90 minus 15.
What?
60.
About 75.
Guys, it's been a long week.
That's it.
No.
It's only
Okay.
Thursday.
Literally worth it.
Now,
Oh, it was Monday.
Shut up.
Oh.
if you know the gravitational force, which is going to be the side opposite the 75, how could you find the tension? Sine, cosine, tangent, by sine.
Because
So the sine of 75
indeed.
is going to equal the side opposite, which is divided by your tension.
Or we can do cosine of 15.
So, here's the question. When you find the tension, would that have to be bigger or smaller than your FG?
Bigger.
Bigger.
Bigger, because you're finding the
Hypotenuse.
So you know your tension of the three of them has to be the biggest. Now, how could you find the electrical force?
Beautiful cosine.
A squared, what's A squared?
Or
Cosine or something.
cosine of
Or something.
75
Or sine.
over your tension. Okay? But here's why I wouldn't do that. Because if you screwed up that tension calculation, you're going to screw that up. I would use tangent. Okay?
Oh, yeah.
That makes sense.
Because tangent is only based upon, so your tangent is what?
Only one.
Opposite, which is going to be
Rowdy.
FG.
over your
FE.
FE.
Right. One value.
That's what I would recommend. Okay,
Mr. Berg is the best.
let me see.
Holy glaze.
You might need this.
Oh boy.
What?
This is spherical.
For what?
No, mom, this way.
Hey, don't say that.
That's a bad word, Mr. Burkett.
No, it's not.
Yes, it is.
Yes,
They look for it.
Yes,
said
it
was.
is.
Yes, it is.
No, that is a bad
Yeah, it
word.
is. Yes, it is.
They look
I'm
for
going
it,
to listen
said
to
it.
Louise on this. Okay?
It's a bad word.
You guys slapped
Louise,
my mother heard.
What is PUTA? Someone called me that.
Shut up, Nathan, for half a second.
Settle down.
Why are you asking that?
Just so you know, Spanish.
Something along the lines.
It's a bad word.
Say what that means.
Female dog.
Okay, that's what I thought.
Oh.
There's no mom's way.
What are we
comment. No comment. No. No.
I genuinely got worried.
Oh! Oh my gosh!